Hi everyone, we're doing exam from 2019. Let's begin. Alright, question 1. Magnetic and gravitational forces have a variety of properties. Which of the following best describes the attraction-repulsion properties of magnetic and gravitational forces? I have a bunch of options here. Alright, well, the one that best answers here is, well, B and C are wrong because those two are wrong, so it's either A and D. Gravitational forces only attract, or gravitational forces either attract or repel. Well, we don't know of any gravitational forces right now that repel, unless you're talking about dark energy or something weird like that. So the best answer there is A. Question 2. The electric field between two parallel plates that are 1 times 10 to the negative 2 meters apart is that. Which of the following is closest to the voltage between the plates? So what do we have? We have electric field strength here, and we have distance. So we have basically the formula: electric field equals what is it? Electric field is voltage per meter, so V equals ED, which is 1 times 10 to the negative 2 times 2 times 10 to the negative 4. Alright, quick calculation off the cuff. 1 times 2 is 2. 10 to negative 2 times 10 to negative 4 is 10 to negative 6. So 2 times 10 to the negative 6. Our answer there is B. Question 3. 3 charges, negative Q, plus 2Q, and minus 2Q, are placed at the vertices of an isosceles triangle as shown below. Which of the following arrows best represents the direction of the net force on the charge negative Q? So we're placing ourselves here as if we were that negative charge, and we're seeing what's the net force on us. So let's look at the force from the plus 2Q charge, so that would be attracting it towards it. So that would go down like that. The force due to the negative 2Q charge, well, that's repulsive, and it would repel away in that direction, okay? And because these two are the same magnitude, these arrows have the same lengths, and so if you've got an arrow pointing up like that, add it to another arrow pointing down like that, same magnitude, there's your resultant. Okay, so the net force is pointing to the left there, so that's option A. Question 4. The magnitude of the acceleration due to gravity at Earth's surface is g. Planet Y has twice the mass and half the radius of Earth. Both planets are modeled as uniform spheres. Which of the following best gives the magnitude of the acceleration due to gravity on the surface of planet Y? Okay, so acceleration due to gravity basically equal to g times m over r squared. So here we are doubling the mass, so planet Y has twice the mass, so we have g times 2m, and half the radius of Earth, so this r is being replaced by half r, okay? Now expanding all this out, you get g times 2m over 1/4 r squared. 2 divided by 1/4 is how many quarters into 8? So that would be 8 overall times gm over r squared. Now if this was the original field strength, then the new field strength is 8 times the original. So our answer there is D. Alright, use the following information to answer questions 5 and 6. A 40 volt RMS AC generator and an ideal transformer used to supply power. The diagram below shows the generator and transformer supplying 240 volts RMS to a resistor with a resistance of 1200 ohms. Okay, there's a picture of everything. So let's have a read of the question. Question 5, which of the following correctly identifies the parts labelled X and Y and the function of the transformer? Okay, so part X is, well, that's where the voltage is coming from, I guess, the variable voltage. So this would be called a primary coil, so it's either A or B. They're both with secondary coil for part Y. So I guess the question is it a step down or a step up transformer? Now that's hinted at by the number of turns on each side. So less turns on this side, more turns on this side. That means it's a step up transformer. So we're going to go with option option B. Cool. Following on, question 6, which of the following is closest to the RMS current in the primary circuit? So the RMS current on this side. Okay, well, let's think about how we're going to answer this. Okay, I think the easiest thing to do here is work out what the current is going on in the right-hand side, and then just transform it back to the primary side. So, the current on the secondary side, let's work that out first. So VS, IS or I2, depending what you are used to, that's equal to IP. And the formula is NP over NS. It's your transformer equation. And so, hang on, no, we're not doing that yet. That won't help us, because I don't know what the primary current is. We're trying to work out the secondary current using the values of the voltage and the resistance that's going on the other side. So we've got voltage and resistance over there on the secondary side. So current in the secondary is voltage in the secondary divided by that resistance. There's 240 volts divided by 1200 ohms. And so that's equal to, quick calculation, alright, 240 over 1200, whoa, too many zeros, 0.2. Alright, now our primary current is just going to be our transformer equation now, so IS NS over NP, that is equal to 0.2 times, okay, number of turns, 6,000 and 1,000, so 6,000 over 1,000, so 0.2 times 6, that's 1.2. There we go, so option C. Question 7, the coil of an AC generator completes 50 revolutions per second. Okay, so that is a frequency. Frequency is 50 Hertz. The graph of output voltage versus time for this generator is shown below. Which of the following graphs best represents the output voltage if the rate of rotation is changed to 25? So we're halving the frequency. Alright, so according to this equation here, E is equal to negative N change in flux over change in time, basically Faraday's law. If you halve the rate of rotation, then this quantity doubles. Okay, it takes longer for it to complete a rotation, right? So we're doubling the denominator, which means overall we're halving the EMF. So you can expect our graph to like shrink down to half the amplitude. So it's either going to be A or D. Now, what also happens is we're changing the period. Obviously, we're doubling the period, which means it takes longer for a rotation to occur, and so compared to the original graph, everything's going to get like stretched out that way by a factor of 2, which corresponds to option D. There you go. Question 8, an electrical generator is shown in the diagram below. The generator is turning clockwise, as you can see here. The voltage between P and Q and the magnetic flux through the loop are both graphed as a function of time, with voltage versus time shown as a solid line and magnetic flux versus time shown as a dashed line. Which of the following graphs best shows the relationships for this electrical generator? Okay, so we've got a generator turning, and we've got a flux and a voltage graph sketched on the same line. Okay, just make a note, these are slip rings, so you can expect the EMF to be sinusoidal, voltage, and that immediately rules out, I guess, D. Now the question is, which of A, B, and C is it? So, at the point shown, magnetic flux is a maximum. So I guess if the graphs are starting at the point shown, then the magnetic flux would have to be starting at a maximum. So that forces it to be options A and C. And then I guess you just need to know from theory that the voltage graph is the rate of change of your flux graph. So the rate of change of your flux graph is 0 at this point, and so the voltage is going to be 0 at that point. Alright, so that rules out option C, so the best answer there is option A. Alright, question 9. A monochromatic light ray passes through 3 different media as shown in the diagram below. Cool. Assume that V1 is the speed of light in medium 1, V2 is the speed of light in medium 2, and V3 the speed of light in medium 3. Which of the following would best represent the relative speeds in the media? Okay, so you can see there's some refraction happening here. Now, what we normally say is that if your light bends towards the normal, you're going from a lower refractive index to a higher one. So that means N1, we're saying N1, N2, and N3. We can immediately say that because we're bending towards the normal here, then N1 is less than N2. And here we are bending away from the normal, which means that N3 is less than N2. So now the question is if both N1 and N3 are less than N2, which one's the smallest? Okay, so I mean, just look at the direction that each light is traveling in that medium. In medium 3, it's bent the furthest away from the normal. So that to me tells me that N3 is the smallest, then N1, then N2. Now just remember, refractive index tells you how much slower light goes in that medium. So the smaller the refractive index, the faster light travels. So in order to flip this around for velocities, you basically say V3 is greater than, sorry if you can hear that in the background, my son is shaking something. V3 is greater than V1, which is greater than V2. And so that tells me the answer is D. I'm going to pause quickly and try and take this bloody rattle or whatever he's got off him. Okay, now that's stopped. Let's continue. So question 10. The horizontal face of a glass block is covered with a film of liquid as shown below. A monochromatic light ray is incident on the glass liquid boundary with an angle of incidence of 62 degrees. The minimum value of the liquid's refractive index, so that some light will just cross the interface into the liquid, is closest to what? The minimum value of the liquid's refractive index, so that some light will just cross the interface into the liquid. So the wording here tells me we're dealing with some kind of critical angle. Okay. So just cross into the liquid means that we are, if we continue the normal, that your light ray just goes in. Okay, so it's just refracted in, it's at the critical angle. Okay, the question's a critical angle question. So we've got, for a critical angle, we have sine inverse of N2 over N1. So in this case, we're solving for N2. Okay, the liquid's refractive index. Oh my god, he's got the rattle again. N2 is equal to N1 sine of our critical angle. Okay, and so the critical angle here is 62 degrees. That's the whole point why that's there. So that's N1 is 1.75 times sine 62 equals, calculator, 1.75 times sine of 62, 1.55, let's say. So that's B. Question 11. An ultralight airplane of mass 500 kilograms flies in a horizontal straight line at a constant speed of 100 meters per second. The horizontal resistance force acting on the airplane is 1,500 newtons. Which of the following best describes the magnitude of the forward horizontal thrust on the airplane? Okay. So we've got some keywords in here. It says horizontal straight line. Okay, so it's not moving up or down. Constant speed. Okay, so it's not accelerating. Let's draw a picture just so we make sure we understand what's happening here. So there's the plane. Right, obviously gravity's acting on the plane. If it's in a horizontal straight line, then there must be some kind of thrust being applied by the wings. Then you've got the resistance acting on the plane, but the fact that everything's horizontal straight line and constant speed means that all the forces cancel out to be zero. So this forwards thrust has to match the, I guess, the resistance acting on the plane. So if it didn't match, then it would be either accelerating or decelerating, but we're horizontal straight line at a constant speed. So that tells me the answer is going to be A. Exactly 1,500. Question 12. A small ball is rolling at a constant speed along a table, horizontal table. It rolls off the edge of the table and follows the parabolic path shown in the diagram below. Ignore air resistance. Which of the following statements about the motion of the ball as it falls is correct? So we've got options here. The ball's speed increases at a constant rate. The momentum of the ball is conserved. The acceleration of the ball is constant. The ball travels at constant speed. Okay, so here we'll just evaluate each one at a time. The ball speed increases at a constant rate. Is that true? I don't think it's a constant rate because you've got both horizontal and vertical components, so I don't think it would be a constant rate. The momentum of the ball is conserved. Well, it will start speeding up. So the ball will speed up, so momentum isn't conserved. The acceleration of the ball is constant. Now that's true because, I mean, there's no horizontal acceleration, but there is this vertical acceleration due to gravity, and that's a constant. Okay, that's just g equals 9.8. So that's the most correct answer so far. The ball travels at a constant speed. That's just wrong because it does speed up in the vertical direction. So I think C is the correct answer there. Question 13. Joanna is an observer in spaceship A, watching spaceship B fly past at a relative speed of this. She measures the length of spaceship B from her frame of reference to be 150 meters. Which of the following is closest to the proper length of the spaceship? So just make a note. Proper length is always less than, no, always greater than, sorry, the contracted length. So proper length is going to be smaller than 150 because, oh, sorry, greater than 150. Sorry, the sun is crying, so I just need to pause for 1 second. Okay, sorry about that. Let's start this question again. Alright, so which one of the following is closest to the proper length of spaceship B? Spaceship B. So it's saying that Joanna sees spaceship B fly past. So Joanna measures the contracted length. Now the formula relating contracted length to proper length is this. So the 150 meters is the contracted length times gamma, which is 3, will give us the proper length. So that's 450 meters. So we're going to claim it is option C. Right, question 14. Electrons of mass this are accelerated in an electron gun to a speed of this. The best estimate of the de Broglie wavelength of these electrons is. Alright, so straightforward calculation. De Broglie wavelength is h over p, or h over mv. 6.63 times 10 to the negative 34 over 9.1 times 10 to the negative 31 times 1 times 10 to the 7. We're ignoring relativistic effects here. That is equal to 6.63 e negative 34 over 9.1 e negative 31 times 1e7. 7.2 or 7.3 times 10 to the negative 11. 7.3 times 10 to the negative 11. Question 15. Electrons pass through a fine metal grid forming a diffraction pattern. If the speed of the electrons was doubled using the same metal grid, what would be the effect on the fringe spacing? Okay, well, according to the equation we just wrote down, wavelength is, I'll say, proportional to 1 over v, and so if the speed was doubled, then overall the wavelength halves. Now we also know that diffraction is proportional to wavelength over gap width. So if we half the wavelength and keep the gap width the same, then overall the diffraction would decrease. Okay, so I guess they wouldn't spread out as much, so the fringe spacing would decrease. So we'll go option B. Question 16. Students are conducting a photoelectric effect experiment. They shine light of known frequency onto a metal and measure the maximum kinetic energy of the emitted photoelectrons. The students increase the intensity of the incident light. The effect of this increase would most likely be what? Well, we know from the photoelectric effect that increasing intensity of light increases how many photoelectrons are ejected, and then that in turn increases the photocurrent. But we also know that from the photoelectric effect that the intensity has nothing to do with the energy. So the energy that the photoelectrons have after being ejected doesn't change, and so the stopping voltage wouldn't change, or the kinetic energy wouldn't change. So kinetic energy does not change, but more electrons are emitted, so that seems to look like option D there, so we'll say D. Question 17. Which one of the following is true when incandescent light is compared to laser light? So this just comes from just your theory that you should have on your cheat sheet. Laser light has a very wide spectrum. No, that's wrong. Incandescent light has a very narrow spectrum. That is wrong. Both laser light and incandescent light have very narrow spectrum. No. Laser light is incoherent. Incandescent light is coherent. No. And D is the only one that I haven't said no to yet, so it looks like it's going to be option D. And that is correct. Okay, use the following information to answer questions 18 and 19. As part of an experimental investigation, physics students use a pendulum as shown below to indirectly measure the magnitude of Earth's gravitational field at their location. So there's a pendulum, and they're just, I guess, rocking it back and forth. The students use a constant mass and a constant amplitude of swing, changing only the length of the pendulum and then measuring the time for 5 oscillations. They obtain 4 different time readings for 4 different lengths of the pendulum. By using the relationship here, where t is the period and L is the length of the pendulum, the students obtain 4 values for the magnitude of Earth's gravitational field. Right, that's a lot to take in, so you might need to reread that again. Question 18, which of the following best identifies the independent, dependent, and controlled variables in the student's experimental investigation? Okay, so it tells us that we have a constant mass and constant amplitude. So controlled would be mass and amplitude. So it's either A or B. And what are we changing ourselves? So we change the length of the pendulum and we measure the time. So we change the length, measure the time. So independent is length, dependent is time. So we're going to go with option A. Oops. All right. Question 19. Which of the following best explains why the students measured the time for 5 oscillations rather than the time for 1 oscillation? Okay, best explains. 1 oscillation is too quick to see, maybe. 5 oscillations reduce the effect of air friction. Don't think that's true. If anything, it increased the effect of friction. 5 oscillations reduce the uncertainty of the measured period, or 5 oscillations reduce the uncertainty of the measured length. Well, D's wrong because oscillations have nothing to do with like measuring the length. I'd go with option C. So basically what you're doing is you're instead of trying to quickly catch one period, you measure 5 periods. So okay, let's put it like this. Let's say your reactions are slow, right? Let's say your reaction time is 1 second. I'm exaggerating here. So if your period is 5, again I'm exaggerating. If your period's 5 seconds long, and your reaction time is 1 second, right? Then your uncertainty is like 4.5 to 5.5. Yeah. Now, if you're measuring 5 periods, that would be around 25 seconds, but your reaction time is 1 second. So for 5 seconds of measuring, you would have a uncertainty between 24.5 and 25.5, but then you're dividing that by 5 because you only want the measurement for 1 oscillation. So you're reducing your uncertainty by a factor of 5 there. So that's why it's option C. Question 20. As part of their physics course, Anna, Bianca, Chris and I'm not even going to pronounce that, investigate the physics of car crashes. On an internet site that describes what happens during car crashes, they find the following statement. Okay, so read the statement, pause it, I'm not going to read it out. The students disagree about the use of the word forces in the statement, that crumpling action works to absorb some of the initial crash forces, protecting the passenger compartment to some degree. Which of the following students best identifies the physics of how the crumpling action protects the passengers? Okay, so Anna says it absorbs some speed, Bianca says it absorbs some kinetic energy, Chris says it absorbs some momentum, and this person says there's no change, they don't need to change the statement, so it absorbs some of the forces. Well, the whole point of a crumple zone in the car is basically to increase the time of the impact, the duration of the impact. Okay, and also what it does is by crumpling the car, the very act of crumpling requires some energy to do that. Okay, so by crumpling the car, the crumpling action basically takes some of the kinetic energy away from the crash, and it reduces the amount of kinetic energy which is then transferred into the occupants of the car. So I'd go with option B here. It just makes the most sense. Momentum is a nice one, but I wouldn't call it momentum. You're not really absorbing momentum. I think just option B sounds the best there. Simply because it takes kinetic energy in order to actually change the structure of the car, to crumple that crumple zone. Alright, and now that's it for part A. So stop here, and in the next video we will start part B.